Okay, now the microphone should work. Let me just check also in the audio my feedback. Why don't you remember that's the other one? Oh, don't know. But let me just listen to myself if the audio works. So, again from the beginning on. This stream is about debugging. In the last stream, we had an issue still about the USB hub. Last time we had an issue because of the EEPROM, and I wasn't able to program it. This was simply because, well, it's quite stupid, but I didn't put the USB controller the wrong way around. The pin 1, instead of being here, it was here, so it couldn't have worked, and I wasn't able to program the EEPROM. That's been fixed. Still, it doesn't enumerate correctly. It enumerates from time to time, but then it got lost and so on, and we checked rapidly last time that we don't have the 24 megahertz clock going into that. And I decided, well, because debugging is part of product development, let's just have a debugging session. Could be boring, could be interesting, but yeah, just have a debugging session, and I want to continue with this product. About the clock, I already had a problem with the clock on the last design. Let me get the last design. This one on this design. And you see I even unsoldered the clock, and I've added these two leads to inject a 24 megahertz clock signal. This was the way to be able to start it. And I thought that the problem was because I didn't have the right capacitors. I had 18 picofarad capacitor, although the crystal is spec'd at 20 picofarad, and there was a copper plane just below the traces, and maybe it would have changed impedance. But it turns out that here I removed the copper, so there is a copper clay. The second layer, because this is a 4-layer board, the second layer is a complete copper fill, except just right here, just below the clock track. I removed the copper because I thought this could change the impedance. I also now used the right capacitors, so 20 picofarad, and it still doesn't work. So there's something I'm misunderstanding about the clock, and we'll try to debug it together. Could be boring, but yeah, I wanted to live stream it still. Sadly, I have no one in the chat right now helping me, so I will just discover myself. And I like debugging stuff. I think this is the challenge that makes you happy when you solve it. Takes time though. So let's do it. I've learned, so I'm completely unfamiliar with, well, completely unfamiliar. I only used clock. I never had to debug clock, so I'm quite unfamiliar with the topic. The only thing I know is that you could have there are several type of clock sources, or you can inject just a square wave, you can inject a sine wave, you can have a ceramic resonator, and you can have these crystal oscillators. So this is a crystal inside that resonates at a particular frequency, a specified frequency. In this case, it's 24 megahertz. And to think, so now we have to test, and yeah, so I tried with this board. So this is to find out how clocks work. So I use this board. This is a blue pill, just a microcontroller with a 8 megahertz clock, and on the back here, so yeah, this is a label because this is a rebadged, relabeled microcontroller. It's not a genuine STM. There's an episode about how to identify genuine STMs and not. And here we have 2 pins, so we can probe the clocks while it is running. And let me show you the oscilloscope. So we don't need the DMM for now, because you cannot measure, as far as I know, I'm not an expert on the topic, but you cannot measure crystal oscillators using a DMM. So let's switch this off. We will need the oscilloscope, and here it is. And we probably don't need this one. So, which, yeah, you probably can see it on the oscilloscope. I have, yep. So, if I connect ground to ground, then I power the device, wrong way around, up. So there's a LED. This is just a stupid firmware which just blinks the LED. There's nothing behind it, but it starts this external crystal oscillator. You don't have to on microcontrollers. Very often you have an internal oscillator which is not precise and not fast, but it is there. And if we look at, oh wow, this is super clear. If we have a look at the sine wave, at the clock, we see it's very, it's a very clear signal. Let's try to trigger on it. Actually, so there is a DC bias on this. There's a DC bias on this clock. I think because you have somehow, I don't know how they excite the crystal, but the idea is to excite the crystal and it only resonates at a particular frequency. And then the microcontroller reuses this frequency to reinject it to amplify the signal. So let's, and this is why we have the DC offset. So let's change that and have an AC coupling. This will remove the DC offset and we can see the clock and we can also see the measurement. It's 8 megahertz, exactly what we want. If we look at the other one, this pin, you see is it higher? Do I have ABP? This is 1.5 volts approximately. No, not 1.5, 0. Let's measure vertically. Vmax, show me Vmax. 760 millivolts. 600, so exactly. It feeds in frequency 24 megahertz, and only the 24 megahertz part is amplified, and it is amplified a lot more, so it's 760 millivolts, and then it probably retakes to again re-amplify, because the microcontroller in the beginning doesn't have an 8 megahertz clock it's put in. I think if we remove it, now let's try that. I'll remove the clock and I'll check what it does to initiate this clock. Here it has issues now. Because ground isn't connected. So I just switch on my desoldering gun, and we will check what it does. It takes a bit of time to heat up. I also have the other probe, this one, which can actually show the DC offset. So here we have clock. Here we see the offset at 1, 2, 2.5 volts, and here we have the same offset at 2.5 volts, but it only takes the AC. Maybe it decouples it inside. I have no idea how you can use oscillators. So the desoldering gun is heating up. Since I will need to resolder it, I will also switch on the soldering iron. And yep, while this is done, so this clock, what I mean with it's oscillating, here I have a bag of 16 megahertz clock, and actually they will be useful to understand what's going on. And here I have a frequency generator. This is the one I built specially for injecting 24 megahertz into the previous board. It's based on an AD8950 module, which can generate a clock over a wide range, which is quite useful. So I need some leads up. So we will have the sine wave going into the crystal oscillator. We will have one side input. Up, it doesn't hold too well. Up, so now it's switched off. Okay, it is switched off. This is the input. Then the output goes to this probe and to the signal oscillator, to the oscilloscope. So this is sine wave output. So this chip, this generator can generate square and sine waves. And now the output of the oscilloscope, the ground, is going to the ground of the clock generator. And yeah, we can connect this to the other ground, so they have a common ground, even if they're connected in the oscilloscope. So right now on the oscilloscope we see nothing. This is because I didn't switch on the generator. If I switch on the generator, we should see, yep, blue is the input. At the input we see it's a 24 megahertz clock, and then yellow is the output. This probe is the output, and we see the signal is not amplified. And now if I change the frequency, like 22, 20, we see normally at 16 it should, yeah, at 16, because it's a harmonic, it's, you see, well, yeah, at 17 the signal is not amplified. At 16 the signal is amplified a lot. So the scales are not the same. One is 500 millivolt, but the other 200. But you see a huge difference. Normally, if we arrive at 8 megahertz, this is 8 megahertz. Why doesn't it work? It should resonate at 8 megahertz. There's something going on. Off, on, 8 megahertz. Oh, it's not an 8 megahertz, sorry. 8 megahertz clock, yeah. So I was right. 8 megahertz clock is was on this board, on the blue pill. This, you see at 8 megahertz, it does nothing. It is a 16 megahertz clock. And if we have, so 14, 15, and then 16, and it resonates. So the signal, 24 megahertz signal, which the 16 megahertz signal which you put in, is kind of amplified because it resonates in the frequency. So this is how it works. And probably, and I don't know how microcontrollers do that, how they inject it. So let's desolder, let's cut the power from this. Let's desolder this clock. Okay. If I remove the clock up, it's quite robust. It's okay. And now what happens if I power and if I probe? What will I see? That will be interesting. Let's use not the AC one, but the DC one. So here we have ground. That's ground. Yep. Tech. And here we have power. So let's apply power up, and let's see on the oscilloscope what we see. I think this one was the input, and it's just at 2 volts. And there is no 24 megahertz, there's no 8 megahertz input. So it doesn't inject 8 megahertz and expects to have a clean 8 megahertz output. I don't know how it does. When I press reset, it's still at 1 volt because of, okay, now 0 volt, and if I remove it, it just goes at 2 volts. How does it, just by putting 2 volts, it expects that it starts. That's super weird. Let's see if it works. Probably there's kind of a, yeah, I think there is a feedback going on where the signal is all the time amplified. This is why it always, when you look at datasheet, it takes time to wake up because the clock needs a bit of time to oscillate correctly, to stabilize. So where is here this thing? So now we have one pin connected. This is the one of the input. Let's check the other one. The other one is also at 2 volts, but there's no signal going on there. Now we have one side connected, one side of the clock connected. Let's see if this is enough to make the oscillator oscillate. Nope, there's nothing there. It's not connected correctly, but yep, there's nothing there. Now if I connect both and then I can check the other side. Let's see if now there's something. Nope. So it really needs both sides to be connected, to be on. And now if I have both sides, I probably need to reset. Doesn't make a good connection. Now it works. Well, it's not blinking. This is a bit too loose. So let's. It doesn't. We see that it puts in a 2 volt signal, not something which is already oscillating. Let's solder it back on and let's try to figure out how it starts by capturing the start of the oscillation. So let's solder the clock. And this way we can try to understand how crystal oscillators work. Okay. I can switch off the desoldering gun so it's not too loud. Let's put this back in so we're sure it's not clogged inside. Well, do I solder some cables on that, because else it will be a pain. I don't want to hold it all the time. Yeah, I'll solder some cables. Dupont wires, something like that. Yeah, I'll solder, or some leads. It would be nice if it would have longer leads. Do I have an 8 megahertz with longer leads? This is 16. This is 8, but this is SMD. That's not a clock. That's not a clock. These are just microcontrollers. I think I don't have 8 with through hole. Nope. So we'll just solder some leads to it. Just get some capacitors, some resistors. There we have leads. Let's see how this looks like. Oh, I know something I did not do, but I think I don't. Could this be the, no? Okay, I have a. Okay, we'll see when we get to the to the USB hub, and when we try to debug the USB hub, one source that could be an issue. I would be surprised if this would be the issue, but maybe it is. So here we have super long leads. Does it still work with such long leads? If it blinks, it should blink every second. Oh, it does. With these super long leads, it's still halfway stable. So I think this is the input, so this is the output. Check, check. And what we can trigger, we need to be connected to ground. This is ground, this, damn it. I'm not strong enough. Up. Let's try to relieve a bit of tension. So here we have ground connected. This is also ground. Now power. And okay, the leads are a bit too long. Now it's not able to start. And we changed the impedance because we've added some capacitance, the leads on it. And I'm shorting ground in 3 volts. This might be another good reason. Let's try to shorten the leads. Okay. So we have the input and the output. We see the voltage offset. So let's trigger. Let's trigger on this and then normal trigger. Actually not normal, but single. If I let go, okay. Let's see how it starts the oscillation. Single. This is too late. So this is off, single. Yeah, I want to see the complete beginning after the reset. Why do you trigger so late? Okay, let's trigger on something else. Menu, trigger menu. Let's trigger on channel 2. The slope is going up. We see it provides 2 volts at the beginning. Slope is going up. And the trigger is at 555 millivolts, and you don't have USB anymore. You're not seeing what I'm doing because OBS crashed again. So let me start OBS streaming. And we are back. So my USB, probably because I shorted the USB. So let's try single. Tack. Ah, there we see the ramping up. Tack. But it doesn't oscillate yet, so let's start again. Tack. Okay. Single. Tack. So this is the boot up. We see it starts to apply 2 volts. And then there's a huge swing, but it doesn't start yet. It's also because the bootload, the startup routine is... So let's go a bit later on. I don't start immediately. So I think it provides 2 volts to the oscillator, even if I don't initialize it. and then the code initializes it, but it's not immediate. It's not even there yet. Let's see how long it takes. Okay, still not. Tuck, no. Wow. When does it start oscillating? We see the decay. I don't know why there is a decay. Still not. So it takes more than 500 milliseconds to start the oscillator. Okay, now it doesn't see the start of the oscillation. I'm pressing on the reset button on the time. No. Wait, but now it triggered, but this is the wrong trigger. We don't see the oscillation again. I think I have to increase this to see the oscillation correctly. Signal up. Why doesn't it trigger? Okay, now it triggers. But we're not capturing the oscillation start. I know why there is this huge spike. It's because of the AC coupling of the channel. So maybe there's already the DC. So and then it equalizes. So the getting down is because the AC input of the oscilloscope is catching up. This is why we have this huge spike at the start. So maybe there is already actually the oscillation on there. So channel 1, let's remove this AC coupling. Let's leave it at DC coupling so we don't have this issue. And let's single. Yeah, it's already there. It's just not visible. I think it's already there. Let's zoom in. Not yet. So it's not as fast as I thought. So somewhere here will be the oscillation. Okay, so it still does take a bit of time to start. Let's try in milliseconds. Can we see it here? Yeah, here it's already there. It's really small. Here it starts. You see tiny bumps all the time. Here, somewhere around here is the initialization. Yep, There's already the clock. Okay, so it's even before. Where's the mode actually? Yeah, because here, because of the signal is higher, it's just because of how the way it is displayed, we don't see correctly vectors. There are modes, vector, no, dots, vector. There was, I think, in the oscilloscope, there were ways to display persistence, minimum, brightness, intensity. How is this called? Acquire? High res. Maybe it's peak detects. Ah, now we see it a bit better. Average. Peak detects. What is normal? High res. We don't want high res. We want normal. There we see the oscilloscope starting. The oscillator starting. Up. And you see the blue line. That's the. I think this is the input, and because it is a small amplitude, and the yellow line is the output. So how does it start the oscillation? Let's try again. Single. Deck. So somehow it just takes time to amplify. It tries to re-inject the signal, and then we see it does amplify. It is really small. See, it's small. And then now it should start. Yeah, now it starts to feeding it back, probably something like that, and then it gets amplified even more until we have a stable signal. And it takes around 400 microseconds. That's faster than expected. Yeah, 1 millisecond is still slow. Yeah, 1 millisecond, something like that. It expects the signal to be in 1 millisecond there. So yeah, there's probably a special circuitry which is there to. It probably generates noise in the beginning on or something around 8 megahertz, but very noisy, and then it expects the oscillator to filter out the 8 megahertz, and then it re-injects it, and then it stabilizes. That would be my guess. How it does that, I don't know, but we see that it's not from beginning on the right frequency. It just amplifies with the time. So that's the start. So this is how we know about oscillators. So now, this is done. So we know a bit more about oscillators. Let's remove these pins because I don't think they're a good idea in general to keep them up. And this board still works. Whoops, I did solder while it was running. Okay, up. This is done. Now we know what we can do is test if my oscillator, if this crystal is actually a 24 megahertz crystal. What we do is again inject to 24 megahertz, and I did prepare, yeah, here. This is one of them. This is with just 2 leads on the 2 inputs. And also what I wanted to test is if I did the footprint correctly, if the 2 pins are correct. So let me get the datasheet so I can show you what I mean. Where's the datasheets? Datasheets. That's the clock. we are putting the clock here. This goes here. Let me show you this one. That's the data sheet, and here we see what it still happens to me to have this issues most of the time because it's not written. Here is the top view, this is the bottom view, this is the top view. What is good is that there's a corner which is pin 1, and pin 1 is the one side of the oscillator, pin 2 is the other side. The two other corners are ground and they are connected to the outer shield. This is to have to kind of shield the oscillator, the crystals, so it's immune to external noise, something like that. But at least it's... So this is the footprint. What's good is written, this is the top view, so from bottom up. So the footprint should also look like this. Now, if we look at our footprints from our board, did we do it correctly? This is a part I didn't use before. So this is not a footprint I've confirmed. So it might be wrong. Let's check it. Full screen is here. Back. So we have, so this is pin 1. Pin 1, this is a clock. It's one of the two clock signals. Then we have, is the numbering correct? Pin 1 on the same side, pin 2, yes. Diagonally pin 3. And the other pin, this line is the other pin going there. So this is, the footprint is correct according to the data sheet. And because this is the bottom view matches the top view, so the datasheet doesn't seem to be wrong neither, but we can still test it. So pin 1 is the one with the corner, and then we have pin 3, which is on opposite. So let's try on the bench if this is also what we see, and this is what I've soldered here. So pin 1 is the white wire, this is the one with the corner chipped, and this is pin 3. And normally if we inject the sinus here, and now we can make it running automatically normal. Let me change how this works. The oscilloscope you trigger again on channel 1, which is not AC coupled. Let's AC couple it. It makes it easier to trigger. So channel 1 is the yellow one. And up, up, up. And duck. One is around here. Why, when it's AC coupled, the voltage so high? I don't know. Maybe this is where it triggered. So we have one side, we have the other side. I also want to monitor the input. So let's connect the input. Let's connect the ground. Kind of connected, and let's put it to ground here. So currently we have no input signal. The input is in blue. If we have there, okay, the ground clip isn't perfect. Up. Okay. In blue we already see some noisy, but it's some 24 megahertz, and in yellow there's nothing. It's very noisy. And in yellow we have nothing particular. This is because don't have the right frequency. Let's change it. This is 17 megahertz, 18. It's already trying to do something. 19, 20, 21, 22, 23, 24. It should, yep. it resonates at 24 megahertz. We see the output is amplified. Still, have in mind that this is one, they don't have the same scale, but even if they don't have the same scale, at 24 megahertz it oscillates. So this clock seems to be 24 megahertz clock, not an issue. Probably this one is defect, but I don't expect so. What we could do is also, so this is powered. Let's power the switch off. I've soldered the cables on the clock, well, actually the capacitors of the clock. So we can also inject 24 megahertz inside and see if it's at the output. So ground, let's switch off. We have ground, we have the sine input. Okay. Let's put it 24 megahertz. Let's use U. Let's connect 1 to ground. This is ground. Pin 1 should always, well, I very often do that. Pin 1 is ground. And now if I probe the output and I switch it on. So let's see if there's signal going in. Yeah, there's signal going in, 24 megahertz, not exactly, but close enough. And on the output, there's nothing. Oh, there is. And it is an amplified 24 megahertz. It is. So here we have 180 millivolts. And at the output, we have 420 millivolts. So this shows that a couple of things. I've soldered it correctly. I've soldered it correctly. The crystal is working and it is at 24 megahertz because it is amplifying the 24 megahertz signal. And the pinout is correct. So let's now see why this USB hub is not able to have to switch on the 24 megahertz crystal, or why doesn't it start it? So this is off. Now, yeah, still ground. And now let's check what it does in the beginning. Not using this one because this is AC coupled. Let's use the DC coupled one because I think it also starts. We have leads, which adds capacitance, but I don't think this will make it important. So this is the inputs. Now normal, it triggers on the wrong one. Menu, let's trigger on channel 2. Channel 2, when you go above 550 millivolts, that's okay. Okay, now if I switch on, we should see it trying to switch the oscillator. Yes, it does try. This is far too slow. Okay, let's try it again. Huh? There is a... Does it work now? Does it work? Let's try with the... So this only triggers at the beginning. Let's try with this one. This is AC coupled and we can trigger all the time. Let's try to put in auto mode. Where's auto? Don't trigger just, but show it all the time. Okay, now there's nothing. But there was something. Come on. I did see something. This is clearly a clock. Let's have a look at the second pin, just the outputs, and this is the gray one. Gray, and we will connect ground to ground. I need a pin. headers, which are long pin, long headers. Up. This is ground. This is ground. And let's see if there's something input output. Actually, I can even have, yeah, the leads are long, but at least I don't have to hold it. This is the input. Let's switch off, switch on. Okay, I need switch off, switch on. Oh, okay. It tries to switch on, it switches it off, and then switches it back on. This is a weird behavior, and it's pretty fast. Switch off, switch on. Okay, now it doesn't do it. Don't know why I did it once. Okay, now I would be curious to see if we have the 24 megahertz on there. No, we don't have the 24 megahertz. But I saw a signal. Maybe 24, maybe the leads are a bit too long. We did see something. You were there. And after 200 milliseconds, it switches it off. So maybe the clock is okay, but we have another issue. Does it stop the clock to save energy? Nah. It doesn't go to... I don't think it goes to sleep. I mean, it's a USB hub. It's intended to be always powered. Let's capture again. No, it's also not 200 megahertz, 24 megahertz. We did see something. Maybe the cables are too long and it doesn't. Oh, you don't see the 24 megahertz there. Let's try by probing it this way. I just have on the right hand, which you can't see, I just have my hand on the switch on and off button, so I can power and unpower the USB hub. Okay, now we see no 24 megahertz, maybe because this is loaded. Let's try again without. We did see a signal, why don't we see it again? Such a shame, it was working really nice. So it doesn't trigger on the other one. So we know that this one is the input. The white wire is the input because it doesn't trigger on it. So it doesn't provide power, it just expects output. But so we don't see a clock running all the time. See, it stops after a while. So let's trigger on the falling edge, and let's see if on the falling edge there was some kind of signal. Okay, this is the falling edge. The beep which you're hearing is actually when it goes on and off. This is the USB power meter, which tells me if power is there. So a beep shows it's on. so it turns off, but the oscillator isn't on. And so what I didn't do, well, what I was thinking about, I said we'll see once we do it. But we know, we did see at once a signal. I don't know why we don't see it anymore. We saw some kind of clock. Now there's nothing. There's no clock. There's just a voltage. And here I'm at 100 nanoseconds, so I should see something, particularly in this mode. But we see nothing. So it's not able to start the clock. So, what was I thinking about? Let's have a look at, so this we don't need, we know it's okay. Let's have a look at the reference design. Doc, I think here, evaluation board. This is the reference design. Here, this 1 megahertz. I didn't put it because, as far as I know, this is not something which is mandatory. This is something to stabilize and so on, but maybe because it doesn't put, so on the other microcontroller, the blue pill, we saw that it applies voltage on both sides. Here it only applies voltage on one side. Maybe this 1 megaohm is required to actually tell the other side, well, there is a clock signal connected. And just because I didn't put R19, we don't have the signal. So let's have a look at the data sheet here. If anything is indicated in a design or something like that, let's check. It might be as easy as that. Clock, that's serial clock, megahertz clock, external megahertz clock. This pin is connected to one of the terminals. And in all my microcontrollers design, I never put this this resistor. Clock inputs, clock slave. Here it indicates also 1 megahertz. So if it's a crystal parallel resonant, I don't know what parallel resonant means. Resonant, okay, because it's a crystal, because it's a resonator. Fundamental mode 24 megahertz. So it might be just because I'm missing this one, which I don't know. Let's try. I have 1 mega ohm. I think I do have 1 mega ohm. No, 100 kilo. Well, at least in my not spare part, 100 kilo. So 0603, the maximum I have is 100 kilo. So I need to order 1 mega ohm because it seems to be common part. So I'll add it to my sheet of things to do. Order 1 mega ohm. Okay, let's see in my 0805 box if there is 1 mega ohm. I know I have 1 mega ohm as through hole, but through hole is probably not a good idea. I don't use 0805 resistors anymore, and you can see that because I have 3 full boxes of 0803. This is 0805. I almost never use them. I don't have a lot of values. So no, I don't have a 1 mega ohm this way, but I have cheating books. It's these ones. I'm sure there's something in there. Here, this resistor SMD book, which on one side is 0603 and on the other side 0805. They have plenty of common values. 0, 10 ohm. What kind of size do I need? Yeah, 0603. So this side. And there I think I have 1 mega ohm. I would be surprised that in a set they don't provide 1 mega ohm. Yeah, 1 mega ohm. So let's try that. Let's switch off this. Let's disconnect USB. Let's disconnect the oscilloscope. And let's solder a resistor and 1 mega ohm resistor. And it's simply because I didn't follow the design, because it is optional on all microcontroller boards I did. It is optional. This is probably just to help stabilization, or I don't know what it is for. But it's not required, because all the boards I used until then worked perfectly without this. Where's my tweezers here? Where are my tweezers? Let's clean the tip. It was completely optional and it worked perfectly without this resistor. Maybe on this design it doesn't. Maybe it does require this one. So here we have 1 mega ohm. Ah, you didn't see actually what I was meaning, because I didn't show correctly. Sorry about that. Up here. Up here in the data sheet, it tells to put 1 mega ohm. Did I lose the 1 mega? No, it's right there. So what happens if I add this 1 mega ohm? Does it really make the difference? I just added between the two capacitors. Oh, it's so tiny. Oh, damn it. I don't want to burn this cable. That's one side. I think that's the other side. And it does look very hackish, but let's test if this was the reason. So put it back into auto mode, and let's see if we have a signal. Ground, USB. Yes, it's a lot better. It wasn't perfect, but we did see a 24 megahertz signal super clearly. So let's try it again with connecting it this way. Up. And you're going to take this ground. Where is this thing? Up. Normal. Switch on. Oh yes, that was it. I made an assumption. I should have not. And what I should have done is just put this footprint for the 1 mega ohm, and if I didn't use it, then remove it. So don't skip out things like that. And I'm learning it again. Yeah, I made a wrong assumption that it doesn't require it, because no microcontroller requires it. It's like It's like these small capacitors which are there for decoupling. You might think 100 nanofarad is nothing, but it's so important for stability. If you just, it's a bit of a pain to route, but put them on the board. You can still not place them afterwards, but put them on the board. And this seems to be the solution. Annoying. At least I can fix it on the board because it's close enough. And now I would be interested to see, does it enumerate correctly? Let's check if it enumerates correctly. So you also want to see it full screen. Channel control. Yeah, so with the clock you see the clock generator, which this is such a stupid mistake, but not a big one at least. Just wastes a couple of days of work. But this is when you learn things the hard way. Oh yes, and it works immediately. Wow. Wow. That's the issue. Nothing with capacitance. Just me not following the guidelines because I was completely unaware that this configuration is possible. Well, lesson learned. Follow exactly the reference design and you can still correct it afterwards. Don't make assumptions. Okay, that's fun. So I remove the cables. Let's try again. Yes, immediately it works. So probably the other board might have worked also and they need to respin. And there was no issue with the clock. Well, no issue with the clock itself or with the impedance or with the 18 picofarad. That would be interesting to figure out. Does it really matter to have not 20 but only 18 picofarad? Now I have the 20, but could have a board where it doesn't work. And we see that the USB hub is not dead, although I soldered it the wrong way. So it is not fragile. It's good. When you pay a bit more for them, kind of expect it. Next step, well, we can continue. Do I want to continue? Yes, I do, because I'm happy that it works. And I've learned about oscillators. What we can do is solder one of the downstream facing ports and see if this works. And then I need to change the EEPROM to match correctly and so on. But for now, where is my mouse? Here. Bench. You probably don't need this view. This is this, but I could use the DTM, and we don't want to see the oscillator anymore. Yep. Up. So let's solder the downstream, one of the downstream facing ports, the first one, for example. Wow, such a stupid mistake, but I'm happy that we figured it out and that we learned. I love hardware, and I love because generally when something is not working, it's because of you. And with humans, it's the opposite. It's always the opposite way. It's never because of you that something doesn't work. It's never misunderstanding. The other one is still, it's always at fault. Which is frustrating. I prefer bearing my fault. So I need to print out, is it no? Oh, it is still on. I forgot to switch off the printer. I need to print out one of the downstream facing ports. Board. Downstream facing port 1. Up. Print that for me. Cups is not started. Let's start cups. Okay, let's print this page. Yes. Up. And also I've modified my, but it seems to be broken. No, I've modified my DMM script. It should be a lot more stable. We'll see afterwards, but if it's still running, it is a lot more stable than it was before. I didn't do the timeout correctly. See, now that I did a multi-page design, this is a lot easier to read. It's a lot larger. Else, I would have all the thing in one page. What I also, so yeah, this is the clock. This is also working. Let's keep it. And let's put it back in the bag. 24 megahertz. Okay, stupid mistake. Happy to figure it out. Okay. Dupont wires. They go here. Long cables. They go here. Dupont cables. They go here. Table is a mess, but we'll clean it later on. For now, we solder. See, everything is on the left. I have to clean the, well, clean. I have to, every day I spend around half an hour to 1 hour to put back everything into place. It's a lot of time, but at least it's afterwards I know where the things are and I can find them really easily. Well, most of the time, not always. Okay, board holes. There are not too many parts on there. We have resistors and so on. So let's do one after the other. Let's populate from the inside to the outside, flat to long. So R103. I think it's all these parts. R103. Okay, it's, oh yeah, okay. What I did here, what I have to test and I didn't test. What I do know is that we have an overcurrent sensing. This does overcurrent sensing, and I actually measure it. And when it does, when the downstream facing port uses too much current, it reports it back. So I see it on the host side, on the computer. You can see it in the logs, and this chip automatically switches off the output. The problem is that how would you know that the target is disconnected so you can start powering again before doing the sensing? This is why I have these options. So this thing here is now, this chip is now taking care of switching on off. In the first version, I had something like this, which I actually need to improve, but that's another topic. So I just had a PMOS with switches on and off the output. The problem with the PMOS, the problem is that I relied on the current sensing of this fuse, but it was too slow. I did measurements, I don't remember. With the oscilloscope, it is too slow and it drains too much power, and this causes the USB to reset. So what I did add is actually add a proper current sensing, which is an MT 9700. And what this does is it does it switches on and off the power depending on this enable pin, and it has also current sensing and can report and switches off automatically. Yes, and switches off when it is too high. And how much is too much current is set by this resistor. You have plenty of equivalents for this. Some of them, very often on USB hubs, you find this kind of chip which has 2 ports and has fixed 0.5 amps. This is not fixed. I think this goes up to 3 amps. I don't remember exactly. And I've set it to the minimum, which is 560 milliamp. Well, no, it's not the minimum, but it's 560 milliamps, which is okay. This fuse is 0.5 amps, So if the 560 is taken for too long, this fuse will still blow. It just gives a bit of margin. And it also enables, allows me to reuse this resistor value, which is the bias for the USB hub. So I added 2 diodes here to actually measure before or after the switch. So this is considered as a PMOS. So when there's overcurrent, it will switch off the power. This will indicate the oversensing, the overcurrent sensing, the OCS, and this is back. And when it is pulled low, which would be the case, then it's switching off, and then this is disabling this. And the problem, if it's disabling the voltage output because of POV1, this thing will almost never recover. There is an exception, because OCS is pulled up by the microcontroller. So you pull it down to indicate that, that you have overcurrent. So by default, it is pulled up. And what happens is, if this is pulled up, actually it will pull this complete section up, and at some point it would recover. And because this is not, so this will go up and then it would recover, and this will not be pulled down again because, well, if there is no short, here, this wouldn't be pulled down again. So it will go up and indicate that there is no overcurrent, and it would enable to switch again. I've measured it. I think it's 3 seconds or something like that. It really depends on this capacitor. Most of is this capacitor, the 150 microfarad and the 12 microfarad. This small pull-up resistor has to charge these 2 things, which takes a bit of time. The other solution is that I use the diode just right here. So as soon as this is switched off, it will immediately recover, because this will still be at 5 volts. If the fuse isn't triggered, and if the fuse had time to recover. So I have to test these 2 configurations and see which one I want to use. But this is the right way. So this is how you should do it. And the mistake I did: put the 2 footprints, use the only one you require. And this is not what I did with the clock. I should have put the footprint for the 1 megahertz and for the 1 mega ohm, and I didn't. Okay, so back to this board. We have one R103, which is 12 kilo ohm. Where is my bag? I think I don't need these ones. Well, not immediately. I can put this back here because this is done. The 12 kilo ohms are also the bias, and actually it's the one which I'm using. Let's take a pen so I can cross whatever I've placed. Yeah. Okay. Let's put solder on all the pads first. This is the fuse. I recognize our footprints. This is a super tiny Schottky diode. Yep, I'll talk about it afterwards. What's good with this overcurrent sensing and switching is that it provides also feedback, protects against feedback voltage. So if it's switched off and 5 volt is coming from the downswing basic board, it's not going to power the board or doing something else. This is something I didn't add in the 12 volts or the high voltage one. Feedback is not prevented when it is switched off, which is not good. And also what I didn't do is, there are two things I could have improved. Here we have a PMOS which switches off the 12 volt. Let's call it the 12 volt rate. It's the 6 to 24 to 40 volts. So this, if this is switched on, then we power the target. We can remotely switch it off. Because this is a PMOS, it has an internal body diode which goes this way. So 12 volt, which you provide, if this is off, if you provide 12 volt here, it goes through body diode and then it provides target to the voltage. That's not good. So, well, that's not good. It could be improved if I want a really reliable USB supply, because having something which feeds back could happen, but it's quite a rare case. So I could improve this if I want even a better USB hub. The other thing which I could improve is here. The same. This we have the power 1 is the signal coming from the. It is power 1. Yes, it is. It is almost the signal coming from the USB hub, which controls switching on and off the port. And you see power 1 is also the one which controls the output for the USB. What you should do actually is, if on the input there is no high voltage or 12 volts, this will also never be pulled up. And actually I do it because of that. Because if there's no high voltage, then this... let me think about it. If there's no high voltage, if there's no voltage target, this is never high, so it never switches on because it is not pulled low. So yeah, I could improve that. Actually it maybe does it because of this thing. It doesn't do it correctly. But yeah, what I could do is that you cannot enable this output if there is no voltage target. I don't think it does it correctly here. These are super, yeah. If I want to have super improved USB hub. For now, let's just have a USB hub. I think it's a really rare case, but it's kind of my target. Well, I wanted to protect against kind of malicious or buggy USB devices and not buggy complete whole boards. And the whole board in the end should have some kind of protection using the voltage input that it doesn't feed back. But if I want something proper, then I will change it. And also what I will change is this footprint. So let me note it actually. No V target out if no V target out switch enable if no V target in. Prevent V target feedback. Prevent V target feedback. Prevent V target feedback, and that's it. Well, change footprint. Use SMD switch, but I want one which is reliable, which is strong, because you have to switch on and off the power. You will probably do it often. I don't want it to break, and SMD kind of have a tendency to break. This is why I like through hole. The through hole option is just not ideal. Let's see. So, we did the 12 kilo, which is this one, R103. Then we have this Q101, and this is this MT, yeah, this one. I didn't have the time to do the inventory with the new parts because I did the redesign of a board and it took forever. It is a simple board. It just has some LEDs and USB and some USB-C connector, but it's still so much hassle because at some point they were out of stock of the USB-C connectors. So I need to change the footprint because There's no equivalent one, or at least there is an equivalent one, but it costs 4 times more, which explodes the bomb, because I have 2 of them, and they are the most expensive part, even without the 4 times price increase. So I change it, and I'm now using a footprint which is same price, which is SMD, because the through-hole one isn't there. Not ideal, because you can't solder it by hand. So it's not really a super part, but I had no choice. And then when this is the change I did yesterday. And then this morning when I wanted to order, they said, the LED you're using, not existing anymore. So now I had to use another LED. Yeah, supply chain, really crazy. It doesn't hold one day. You can't expect anything for one day to be there. It changes so fast. It was better in the past. So this is done. We have this one, and actually wants to have D106. Why is it so large? D104, D106. What did I use? I used this RBS. The RBS are the one which should be super tiny. Okay, that's not. That's a capacitor. Okay, this is the D106. Okay, now I get it. It's super cramped, so having the seal screen with text. Damn it. Okay, the parts are gone. Don't put it up. It must have happened at one point. No, it's not just resistors and LEDs. It's not too important. Yeah, I can throw everything away. Yep. No point in reusing it. I can throw everything away. Even the capacitors are completely mixed up. Don't put it up somewhere, put it down. Now I learned my lessons properly. Ooh. $10 worth of parts? Nah, not even. But yeah, I can't reuse it. Damn it. Okay. I can reorder them actually, at least. It's for another day. You go here, I'll take care of you another day. What did I want? Ah, yeah, power book, because I want something. MOSFET diodes, I think it was Schottky diode. Yep. These teeny tiny one. Need one of them. And I want it at T106. Let me cut the tape. seeing what I'm soldering. Not good. Yeah, this diode is not super well soldered. This was something else. Let's use this tip. Should have soldered tweezers. This is something I don't have. And I don't know if they're really worth it. For desoldering, it's probably really useful. For soldering, maybe less useful. And for desoldering, if I want to desolder, I just use either the desoldering gun for through-hole parts or just hot air. It's not very targeted, but it's fast. Come on. Not able to solder one of these stupid diodes because it's not flat. And I lost it. No, here it is. But one of the pins is bent. Let's use another one. I won't use this diode anymore. This Schottky diode. It's too small. It's a pain to solder. I'll use something a bit bigger. SUD 523 is just too small. And I have space on the board. Okay, now it's soldered. Next is C125. So we did solder this one. We don't want this one. C125 is probably this one, 10 microfarads capacitor. I think they're here somewhere. So let's. Where are my 10 microfarad capacitors? 1 microfarad, 10 microfarad, did I? Seriously? 10 microfarad, yes. As ceramic. It's huge value for ceramic capacitor. This is what was recommended by the design for these MT 9600s, 700. It recommended 10 microfarad to have them. 150, this I'll use. One microfarads, 20 pico. Nope. That's farad. That's electrolytic. This is a diode. Shrouded. 100. This one? No. Maybe I have some in my other capacitor thingy. Yes, I do have. 10 microfarad, 10 volts, that's good enough. I only need one of you for now. But I don't have nothing. I don't have anything bigger. That's the most I have. It is ceramic. Although I do have, but it is something which I've found from, which is salvaged. So I could use this also, which would normally be used for FPGA boards. What we need is also this kind of diode. So we don't need this anymore. This we will need. We have TVS diode, the 2 bits and not the 4 bits. This one. I need to order more of them. I think I have more of them in another row. Here's the dots. Now I see it clearly. I think the last time there was just not enough lights. Okay, I did create a solder bridge. I think I'll need some, yep. I'll need some flux to get rid of it. There was a copper plane, and this is why it took a bit more effort, and I did put too much solder. Well, normally you stick super well, almost there, to this huge solder tip. Okay, fixed. This is also why I like this solder tip, because it's useful to remove solder. So this is a decoupling. This is the shielding capacitor, well, the capacitor for the shield. So I have one at the input with a resistor, and then at the output I always have a capacitor, which you can add 100 nano. This removes the AC part of it, and the resistor, the only resistor which is on the input, this one removes the DC part. So that's done. Here we have 3 LEDs, and the 3 LEDs I've just lost. And oh yes, here we have the LEDs, but I don't know which one. 103. Did I add the color here? Yeah, I added the color. So let me get the LEDs. SMD LEDs here. We have, so 103 is the power, I think. 103 is green, yeah, it indicates power. Green at 805. This one, and we have the marking, which is a bit more green on this side, and the marking is the cathode. Should be. Else I would have marked it on the tray if it's not the cathode. Then we have 102. 102 103 is placed. This is placed. 102 is red. Red 0805. 0805 so capacitors 0805 LEDs are still less expensive than 0603. I don't know why. Which is different for the resistors. If you buy a bigger resistor 0805, they're more expensive. But somehow this change hasn't arrived yet on LEDs. Where's the pin 1 marking? I think it's this side. Yeah, I think this is the anode marking, cathode marking. But I think at some point also the LEDs, the 0603 LEDs will be less expensive than 0805. And I don't mind having a bit larger LEDs. They're a bit more visible. Although even the small ones are powerful enough. Let's put on this side again. Doesn't look perfect, but looks okay. This is D. Now we have blue, which is 0805 blue. You are 0805 blue. G101. Oh. There I switched the direction, the orientation of this part. Okay. Now, what is this resistor? This is R105. So this is done. R105 is 1K. And since I've lost, so this is done. Resistor, where are the bunch which is less, which is up to 1K, 1K, yeah. I'll fill my tray another time. So, resistor 1K, 5%, that's plenty sufficient for LEDs. It's this one, yeah. Then 106. So 106 is 1K. Oh, was it also 1K? Did I do it? Yeah. 105 and 106, that was 1K. 105, it's down. 106, 1K. Okay. Now we have, I think these are the two from the switches. Yeah, 101 and 102. 101 is 1K again. Oop. There we have it. 101 is 1K, and it's this one. And the other one is 100K. This is the pull down resistor to be sure that by default it's off till it is on. Mm, 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 mm. 100K. Okay. This looks ugly. This is done. So 102 is done. 104, 101 is done. Now we have, this is C104. Ah, I also have at input T 10 microfarad. Okay. Microfarad is really a lot, but I can still, if I'm not happy with it, I can still put something smaller. Footprint is the same. But for now, let's respect the design. We see the mistake. Like with the clock, we see what happens if you don't respect the design. It doesn't respect you. And then you lose. Then you cry. That's done. The fuse, which is in the power book. The power book is not here yet. Power book. Let's have the fuse. And I lost it. Here. Actually, I don't know if I need the would need the fuse because I do have this overcurrent. The overcurrent is not set very high though. So there's how fast it switches depends on how much overcurrent there is. So if 101 is done, now we have all of these. These are always 100K. 100K. 107 and 104. Yep, the two are 100K. 1, 2. It's done. Second one. This one, this is also 100k. And this from the voltage divider. Why did I create a voltage divider? I think I wrote it on the sheet. To protect the gate. Because the gate is maximum 20 volts VGS of this PMOS. And since it goes up to 40 volt input, we need a voltage divider to not exceed the gate limits. And then we have a PMOS. You only see half of my tail, but the other half is also filled with SMD parts. So, PMOS, we have one time the AP4005, 40 volts, 5 ampere. This is actually the limit. This is what defines the limit. It's this MOSFET, and I'm sure some other parts too. It's Q104. It's probably the one. Yep, the one near the switch, well, near the output. Makes sense. This allows us to have short traces. Short traces means least resistance. Least means least voltage drop. Although I could really increase the size of these traces. I think they're already 105 millimeter. They are short, but they could be even larger. Why do I have two? Oh yeah, okay, now I know. And the other one is a BSS 138. It's a very common N-channel MOSFET. Logic and channel MOSFETs up to 200 milliamp, I think, something like that. Yeah, 200 milliamp. And everyone does this one. Okay, now we have also two capacitors. We have, are they the same? So this is done, this is done, this is done, this is done. We have 100 so the 101, this is a 100 microfarad. 100 microfarad. We have different one for 20 volts, 40 volts, and for the other voltage, let's see, 100 microfarad. No, so the 100 microfarad 50 volts, and the other one is 180 microfarad. Not the same. So that's 100 microfarads. This goes here, plus, up, minus. It's not too high. It's a bit higher than the connector, but that's okay. Let's solder one side. Hold it, and then solder the other side. Clip the leads and hold them so they don't go poker eye. Yep, that's on. And we have the other one, which is 150. So this one. Are these also? No, 16 volts, yep. Yep. Ooh, which is minus? Oh, this is minus 150. Tech. And I don't remember where I put the USB. Or maybe I do. USB ports. One after the other. Let's solder this first. Cut the leads. Okay. Now we put switch. Up, we need one, yep, this one. One of the USB ones. I think I didn't change the USB configuration, and it shouldn't be flipped. D plus and D minus shouldn't be the other way around, but we can change the USB configuration. That's not much of an issue. So, starts with this one. Bit of solder to tack it. Solder, go there, use all the flux. I don't care. Just need to tack a contact. Yeah. Okay. I can solder the other pins. This is ground. It's holding. This is input, and actually on the switch I'm not using the output. Oh, it's not, doesn't make sense. I could say on the output I could do sensing of the switch to enable or disable the... Yeah, I could do that. And if nothing is plugged, I could do that. If nothing is plugged in, no power comes out. Could be a good idea. But it's not really necessary. I don't know what it would protect. Yep. Completely not straight. Up. Okay. See, this is the only part which I need to solder this way around, which is not a good idea. Up, let's switch off the oscilloscope. It's noisy, although I changed the fan already. Ah, too noisy. And now, oh, no, it fits. Whew. I should move a tiny bit this capacitor. It's really tight. It's larger than the footprint. Maybe I didn't update it. It's still working, it's just very close to the connector. Okay, this 1, 2, 3, 4. This is shield, this is harder to solder because we have a huge... Yeah, this one's low, although there are terminals. Okay, this is done. Port 1 is completely soldered on. And normally, so edge is on, center is off. So this means it is off, meaning normally there should be no power output. So let's test this thing. Let's test if there are shorts and so on before we power it. Before we write the change the EEPROM and try it out to see if it works. And if this one works, all the other ones they're copy paste. There shouldn't be too much of a problem. So how do I do that? How do I test if it doesn't use too much current? I can reuse this goes here. me just clean a tiny bit the bench. So let's have a larger overview, since we will do some testing and we don't do any soldering anymore. Up. Okay. So we need this USB kind of toy injector. This one. This allows me to current limit it. Up. This is the input. I need, so this is plus. Minus is here. Minus. Now we'll test if this thing still works. I could also clean all this solder. No, let's not do it now. So if I change the voltage, does it change it also on your side? Nope. Maybe because it's not set. Let's see. Set. No, it's broken again. Yep, I also see it. It only reads, it even doesn't read. I don't know what's happening. I thought I fixed it. I did fix something. Okay, 500 milliamp. Let's switch it below. Let's switch 300 milliamp. There should be no thing which uses that much. Let's plug it in. Let's switch it on. 100 milliamp. That's a lot. And no LED goes on, which is kind of not expected. Okay. Did I do it the wrong way? No, this is minus, this is plus. We have 5 volts. So, multimeter. Let's test things out. What is the set probe of the multimeter? Yep. So let's switch on. Let's see if the 3.3 volts are fine. 100 milliamps for doing nothing is quite a lot. No, that's the wrong measurements. 3.3 volt, that's okay. So there's something going on somewhere else. Oh, this light was lighting very briefly. Yeah, now it's on. Why is this on? This shouldn't be on because there's no USB. Actually, this should actually not be on at all. There is no USB connected here. And this should go on. If this is this way, the green LED, this one should be on too. Yeah, the LED. Okay, it works. So it's soldered the correct way. What's going on? Okay, it briefly blinked. Why isn't this one switching on? Why is it consuming 100 milliamp? There's nothing, there's no calculation going on there. What is drawing 100 milliamp? Do I again need my infrared camera to check out what's going on? Now the batteries are charged, so I could use it. I've never tried this piece. Maybe this is wrong. Let's see. Let's probe. So, I want some ground clip. Up. You connect this ground to this ground. So we have a ground chip. Now we can probe around. If I switch on the fuse input, we have 4.8 volts. What's coming in? Let's check the input. Input, there should be some input, 4.8 volts. Okay. The cable drops a lot. That's the USB input. This pin here. 4.9 volts. Okay, we have 4.9 volts input. And then after the MOSFET, 4.8 volts. Why are the MOSFET not switching completely on? So this is the input of the MOSFET, 4.8. Okay, woo. The ferrite bead is dropping something. No. The fuck? The fuse is dropping. This is the input of the fuse, 4.9 volts. 4.95. Output of the fuse, 4.85. It drops 100 millivolts? What the fuck? Because it draws 100 milliamp, it draws 100 millivolts? This is huge. Why is this? What is the resistance of the fuse? It shouldn't be that high, is it? It really drops 100 millivolts. Means that if I draw 400 millivolt, 400 milliamp, it will drop 400 millivolts. That's not acceptable. I don't think I have a data sheet of this fuse. No, I think it's a fuse I bought on AliExpress or something like that. I can just completely shunt the fuse, but yeah, at least we know a fuse issue. Check fuse spec. Check fuse spec. Okay. There's something getting warm. Before, let's get the infrared camera and let's try to find out if something is getting warm. Something is dropping 100 milliamp. Yep, phone is starting. Do I have a short maybe somewhere else? I do have plenty of leads. I don't know where they go. No, but if I would have a short, it would be a short. Oh, there's no short. Come on, phone, wake up. Up, starts. Thermal camera. Okay, so let's check our board. This is reflecting infrared. This is why it's getting warm, because it's metal. You're not seeing a lot. Okay, let's switch on and see what heats up. Nothing on this side. Okay. this thing hits up again. Ah, maybe it is still defective. I didn't test if it heated up after I've soldered all these things, before I soldered all these things. Yup. There's an issue with this thing. Now I don't know if the issue is because of a component here. Did I do something wrong on the output? On one of the connections? I don't know. Let's see if it enumerates. Okay, you up, switch off for now. Does it enumerate? Yes, it does enumerate. Does it get warm when after enumeration? Where's my USB power meter? Yep. Up. Yeah, it draws 200 milliamp. That's a lot. It shouldn't do that. But it does manage to enumerate. I really don't know if I damaged the chip or if there's something wrong with the downstream facing port. I didn't test if it draws. Did I? Maybe if I look at the stream, I see if it draws. I think it has to do with the downstream facing port. I don't think it drew 100 milliamp. So what could be wrong here? Maybe the output LED. This thing. The overcurrent sensing LED. Let's completely remove it. Okay, now the output current sensing port is not connected at all to the output line. Does it help? Up. Yep, that was it. Did I solder it the wrong way around? Might be. Else I don't know why it would. Does it drain? So now it draws only 1 milliamp, which is something which is expected. So let's switch to maximum 200 milliamp. So it has to do with this one. Maybe I switched it wrong. Maybe I put it wrong. I don't know. So let's try to put another one. Maybe it was broken. No. Maybe the polarity was wrong. But wow, lucky guess. Really lucky guess. Schottky diode. Might have just put it the wrong way around and 5 volt was injected into a 3.3 volts device, which it didn't like. Comprehensible. Okay, now I see, and I will test. So it's the other way around. Afterwards, I will still test if it's the right way. Up. One side. Where is my solder wire here? That's the other side, and let's check with the multimeter if it's correct. Up. So we should have this should be plus, this should be minus. Which it's not. Ah, wrong mode. Continuity mode. I want to be in diode mode. Now we're in diode mode. Okay, 0.3. That's a Schottky diode. That's the right way around. If I do it this way around, no, everything is blocked. So this this USB chip is quite resilient. I think I've injected 5 volts on the pins, which I didn't really like. As it heated up, but it didn't damage. Good. I'm happy with it. So let's plug in the USB. And actually I could plug in just a 5 volts. Normally everything powers also from 5 volts. I don't even need to use the USB, but yeah. Whoa. It was on and it was still doing this. Okay. So I didn't solder it the wrong way around. It still draws 100 milliamp. Why? Why would you draw 100 milliamp? This is just pulled up. Clean the other. Well, it's not the fault of the other part because it didn't do anything. Let's try to measure the voltage around this pin, around the Schottky diode. It's soldered the right way around. So I didn't understand the problem. Okay, 100. On the output we have wrong mode. Voltage. On the output we have 0 volts. Okay, and 0 volts here. The hell? Okay, there's something very wrong happening. So it's not because of the... It doesn't seem to be because of the diode itself. The Schottky diode, there's no voltage coming out. This is why also the LED is not there. So, voltage, we have 5 volts there, 5 volts there. It's going here, it's going here, it's going there. 5 volts. And now we should have no output. This is the output. Yes, we have no output. So this is switched off because... Okay, this is center off, edge on. What is draining? What is draining you? Are the capacitors? Did I mix the capacitors and are they the wrong way around? This one is not the wrong way around. This one is also not the wrong way around. Okay, is it? No, this one is not the wrong way around. This one neither. 2 capacitors are fine. They will Okay, the OCS will be a bit low because it will charge. Maybe my design is wrong. By default, let's try. There might be something wrong with the design and I can't put it here. So I think what I fear is at the beginning, the power is not enabled here per default. And we can measure it using the enable pin. So all the power goes through here. It tries to charge, but it doesn't manage to charge. I don't know why. Maybe because everything is going through here. It goes through the USB hub, which is not a good idea. Let's try to measure the enable pin. The enable pin is pin 4. Which one is pin 1? This one should be pin 1. Yeah. The enable pin is at 0 volts. Why is it at 0 volts? Maybe two. Either I'm pulling it low. Because of this switch. But that's there it should pull it low, there it shouldn't pull low. If the switch is as expected. And the other reason is up 102, 101. These are these two resistors. 102, 101. These two resistors. What is power 1? Power 1 is going through 101. Through this one. Yep. Let's see what voltage is here. 0 volts. There's a fault somewhere in my design. So here there's 0 volts. Why is there 0 volts here? See, at the beginning there's a short red. Here there shouldn't be 0 volts. This is power. No, that's the wrong one. Here. Power is enabled by default. Is disabled. When power is disabled, everything goes through the diode. The whole charge. Probably this is the fault, so I cannot put the diode here. Let's try remove again the diode. Okay, now it's removed. I don't want to salvage this one. So let's try again. Yeah, now it's fixed. So it has really to do something with that. I can't put the diode in here. Let's check if the rest is okay. So here, now it's 3 volts. So because I'm not pulling it low. So now the enable pin, power PVR1, that should be the input. Still low. Why is the enable low? That's the enable pin, right? It should be this one. 101 here. This one. Low means off, right? Yeah, power is active high. We're not draining, there's no overcurrent. Because it's the overcurrent pin, this one. Is it? Yeah. Is it 3.3 volts? We're not pulling it low. We're not indicating an overcurrent. So if you're not indicating an overcurrent, why is the power input low? This is this one. It's F105, F101, F101, this one. Why is this one low? This should be high. Switch off, on. Doesn't switch at all. This is also before the switch. So if I put it this way, it pulls it. If I put it this way, it pulls it low. That's for sure. But if I put it, but it's after the resistor. before the resistor, where is actually, here, it's coming from here. Before the resistor, this should be high. Okay, it's not. Which pin is it? Power on 29. This, which one is 29? I have to look at the board. Which one is 29? I don't want to count. Board. Which is OCS1. Full screen. I have too many things in here. I'll go there. I need a bit of space. Okay, so here we have it. What I mean is this, yeah, this one, this is the power input, this is the power line. If we show view, show net names when zoomed in, okay, it shows only when zoomed in. Here, yeah, OCS, this is OCS1, this one, it's SA, I think, no, SC, what was it? Select all connected, CC, CF, no, there's something wrong here. CF, now it finds us all connected, and now I can select them all. I think it's select all SAC, all found object. Here we have the complete path, which is highlighted. This goes directly from here, this pin. This is pin 29. And 29 should be high. That's the fourth one. That's 32. This is 29. 1, 2, 3, 4. It is not high. Why is 29 not high? Shouldn't it be high by default? We can ask USB hub again why it's not this way. This might be some. No, until now it survived. This chip survived everything. 1, 2, 3, 4. Till now this chip survived everything. It would be really a surprise that this pin, which is an output, has been broken. But it can still be possible that the chip is defective on the outswing port. I think it's a design flaw. I rather think I'm doing something wrong. What's sure is that I'm not allowed to put T106, 107, 106. It drains everything through this chip, which is not good. I don't. Again, this could be a fault because the chip is damaged. 5 volt, 3.3 volts, and here we have 0 volts, so it is pulled low. Now I need to connect to USB. Do I have a USB line? Problem is, if I use USB, I cannot control the power. Up. Here I have some USB. Can still use a power meter to check how much it drains. And I have plenty of power meters. I hope it didn't damage any of the video feeds. Let's check. Did it? Yes, it did break a video feed. Yeah, this is why I want a new USB hub. Let me restart OBS. Okay, so the power meter is there, and normally if I connect, I should see the USB hub appearing. We can't get hub status. Okay, why can't you get the hub status? Okay, there's an issue with the hub. Yeah. What is it doing? Is there a short somewhere? Why are you toggling between on and off? Why are you using 100 milliamps now? Fuck. There's nothing which I did short. Why are you using so much when you're starting? It tries to restart all the time. I also see it restarts the hub all the time. But you're not seeing what I'm seeing, but the USB power meter says it goes to 100 milliamp and then off and on again. This is weird. Is it because of the power meter? Let's try a direct connection. No, it's also disconnecting all the time, and this LED is blinking. So it's not because of the power meter. Let me get a long USB cable and let's connect directly to the host, not through any of the devices, of the hubs. Where are my long USB cables? I thought I had one there. No, it's not there. Well, I still have some. And my USB boxes. A to B, USB 2, here. Up. Yep, this seems to be long enough. Up. So, it's connected directly to my host computer. I'll show you what's happening. So this is done, this. So you can also see laptop and mouse here. You can also see this weird behavior. See, it's restarting the hub all the time. I don't know if the host is restarting the hub or the hub is resetting, but something is wrong. And actually, it didn't happen when it was on my bench, did it? Okay, it did. Oh. When the power is on. Now I switch the power off, center off. It doesn't do that anymore. Does it draw too much power at the beginning? And this, are the capacitors too high? And this causes the reset because there's a dip in the voltage. Would be possible. Let me show you. I don't need this anymore. So, if I connect here, everything works fine. It doesn't switch on and off all the... No, it does. Yeah, and it blinks. Now, if I switch power off, edge... Ah, no. Still happens this way. Oh, makes it even more complicated. It was behaving correctly through the hub, and now directly on the host it's not behaving. Okay, there's something definitely wrong with my output. It charged the capacitor. It does charge the capacitor, but it's only... There's no overcurrent sensing. Why does it dip? On the output there is 100 micro, but it's under 12 volt, and on the other one 150 micro. 150 micro isn't too much. Let's use this way. Wrong port. Yep. 5 volts here. If I provide 5 volts here, it doesn't do that. Do I have to check how much it draws in the beginning? And the thing is dead again. That's because the USB is dead. Normally you should detect when there's no activity. Why don't you detect when there's no activity? If there's no activity for 3 seconds, you should reconnect. You should close the connection and reconnect. Why don't you do it? So when I switch power here, it behaves correctly. Does it draw too much in the beginning because of this one cap? I will have 7 of them. If it can't power correctly, I don't know. Yet another issue. Yep. Flashes. I'm not sure if you see it correctly, but the LED flashes and it restarts always the device. I'm sure if I look, yeah, also this one drops a lot. So maybe the fuse. Yep. Now I get it. The fuse drops a lot because of the initial current draw. And because, well, if I do it this, let's try. So that's 5 volts. Here, I provide 5 volts, there's no issue. What if I connect here? Okay, then there's no... Oh, now it works. And oh, the LED is too bright, far too bright. I have to change the green LED. I think I already wanted to change at least 2K. So if I provide external voltage and connect USB, then is the USB hub at least detected? Yes, USB hub is detected and it works correctly. I think the input fuse is causing some problems. There's probably too much capacitance. The input fuse just resets. I think I would have to measure it, but that's for another time. We did advance a tiny bit, we found. So we did solve the oscillator issue. We now went to the downstream facing port. We have issues on the downstream facing port. We know it is power related, and I really need to change this bright LED. It's too bright. Maybe through the case it's not too bright, but for now it is. So yeah, normally, so this is on, this is off. That works correctly. Tack, 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 tack. But it doesn't work just when the USB is powered. Oh, at least, no, it does. I think there is too much capacitance. And when you start powering, so yeah, capacitance dropped. Yeah, I think there's too much capacitance, and the fuse doesn't like it. I think it's the fuse, but this is for another time. Let's end the stream for now. I have other things to do. We did advance and it is moving on. So until next time, until next stream, enjoy the rest of the day. Bye bye.